Hi guys, welcome to today's video, Grade 12 Finance. Without further ado, let's get to it. By the end of this video, you will know how to calculate the time taken for an investment to grow, understand present and future value annuities, learn how sinking funds works, and compare different interest and loan options. This chapter contains significant marks in exams, so make sure you stay until the end because I will be walking you through everything you need to know. Alright, let's jump straight to it. In previous grades, you were obviously introduced to simple interest, compound interest, along with the concept of depreciation. Also, terms like nominal and effective interest rates should also sound familiar to you, and you were told that simple interest is represented by the following formula: A is equals to P, 1 plus IN, where A is obviously your accumulated amount, P is the principal amount, I is the interest rate, and N is the period of the investment. And again, you were told that compound interest is given by the following formula: A is equals to P, 1 plus I all to the power N. And again, simple depreciation, now you just change the formula of the simple interest. Where it was positive, you change it to negative, and hence you will have the formula A is equals to P, 1 minus IN. And you were introduced also to compound depreciation, where again you just change the sign of the compound formula, and you will have the following formula: A is equals to P, 1 minus I to the power N. And finally, you were introduced to this formula: 1 plus I is equals to 1 plus I to the power M over M all to the power M, where you use it to switch between nominal and effective interest rates. In this chapter, we look at different types of annuities, sinking funds, and pyramid schemes. We also look at how to critically analyze investment and loan options and how to make informed financial decisions. Calculating the period of an investment. Solving for N, or the time period of an investment, using the simple interest formula is straightforward enough. We just rearrange the formula to make N the subject of the formula. But when we now try to solve for N using the compound formula, where N is an exponent, it's not as straightforward. We need to use our knowledge of logarithms to determine the value of N. And hence we're going to solve for N in this particular formula, where we have A is equals to P, 1 plus I to the power N, and A, we know that is our accumulated amount, as I've previously mentioned. P is the principal or initial amount, or the amount to start with. I is the interest rate written as a decimal, and finally N is the time period. Alright, let's rearrange the formula now. The formula is as follows: A is equals to P, 1 plus I to the power N. That is the standard formula for compound interest. Now we're going to solve for N, or make N the subject of this formula. The formula goes like: A is equals to P, 1 plus I to the power N, and dividing both sides by P, I will have A over P is equals to 1 plus I all to the power of N. Now from here, to move into making N the subject of the formula, it's not as easy, or it's almost impossible. But with logarithms, it becomes very simple. I'm going to go on and introduce the log, where N becomes the subject of the formula. N is the subject of the formula because it is the power of my equation. And then log base of something. The base, 1 plus I, becomes the base of the exponent N. And finally, A over P, which is on the other side of the equation, goes inside the brackets, which will have A over P. And hence, we'll have the formula N is equals to log base of 1 plus I A over P. Let's move on. Simplifying that formula a little bit, we'll have our base as the denominator. Log of 1 plus I will become now the denominator, and the log of A over P becomes the numerator. Now, let's jump straight into an example. Exercise 1. Tabo invests 5,200 into a savings account which pays 8% per annum, compounded yearly. After a certain period of time, his investment has matured to 6,150,82. For how long has Tabo's money been invested? Let's take a look at the solutions. We know that A is equals to 6,150,82, P is equals to 5,200 rands, and I is equals to 0.08. N is what we're looking for, or the period of an investment. Now, introducing the compound interest formula, we'll have A is equals to P, 1 plus I to the power N, and substituting in everything into my formula, I will have 6,150,82 is equals to 5,200 1 plus 0.08 all to the power n. And again, dividing both sides by p, which is 5,200, I will have 6,150.82 divided by 5,200 is equals to 1.08 all to the power n. Now, when you're here, you might be tempted to divide out the 6,000 and 5,000 there and just, round it off. But I would advise you against doing that before you finish the questions. Wait until the very end until you can round off your answers. Now, let's move on. Here is where we introduce now our logarithms. N is our power or our exponent, and we know that it becomes the subject of the formula. The 1.08 is the base of the exponent, and hence it becomes the base of the logarithm, and that one that is on the left hand side of the equation becomes the subject of the logarithm. Let's write that down, everything I've just said now. N is equal to log base of 1.08 6,150.82 divided by 5,200. And rearranging that formula just a little bit, I'll have n is equal to log of 6,150.82 divided by 5,200 as I've done before, all divided by log of 1.08, which is my base, and that will give you a period of 2.18. Now let's move on to annuities. First, what is an annuity? An annuity is the number of equal payments made at regular intervals for a certain period of time. Present value annuity, that is regular payments made to pay back a loan over a given time period. And next, future value annuity, that is regular payments that are made into a savings account to earn an accumulated amount over a given time period. Now let's take a look at an exercise. For 9 years consecutively, Owen makes an annual deposit of 4,000 Rand into an investment account. The interest rate on the account is said to be 12% per annum compounded yearly. How much money will be in Owen's account at the end of 9 years? Now, I know that my P is 4,000, I is equal to 0.12 or 12% divided by 100, N is equal to 9, A, we don't know, or the accumulated or future amount, we don't know it. That's what we are trying to calculate. And now, this is the type of an example where you have to use timelines. And you can see my timeline below. It is from T0 up to T9. From month 0 or year 0, he didn't deposit anything. But at the end of the year, that is at T1, he started with his regular deposits or his annuities. From T0, there's nothing. Make sure that you understand that. And then from T1, our annuities start 4,000 up to T2, T3, T4, T5, T6, T7, T8, up to T9. He made the regular deposits of 4,000 rands of 12% compounded yearly. Now, to calculate how much money he will have, we need to make use of a table so far. Now, as you can see from my table, from year 1, he made 4,000, year 2, year 3, year 4, year 5, year 6, year 7, up to year 9, he made regular deposits of 4,000 rands. And then, number of interest each amount has accumulated now. The first amount he accumulated spent 8 months in the bank, that is n-1, 9 minus 1 is 8, and hence from year 1 up to year 8, that is 8 years period. Year 2, it spent less time on the bank, hence 7 years. Year 3 made even less, 6, year 4, 5, year 5, 4, year 6, 3, year 7, 2, year 8, 1, and finally, year 9, he didn't spend any time at the bank because at the end of 9 years, that's when he stopped. He didn't make any more deposits and hence the time period has elapsed. And hence it spent 0 years in the bank. And now let's go on into our calculations. Now for year 1, he's deposited 4,000 rands and it spent 8 years in the bank, and hence then N for the first year is 8. And putting that into my compound interest formula, I will have 4,000 rands, 1 plus 0.12, all to the power of 8. And now for the next year, 4,000 rands, 1 plus 0.12 to the power now 7, year 3 to the power 6, year 4 to the power 5, year 5 to the power 4, year 6 to the power 3, year 7 to the power 2, year 8 to the power 1, and year 9 to the power of 0 because again it didn't spend any time at all in the bank. And now punching in all those values into the bank, I'll have for year 1 9,983.85, for year 2 8,842.73, for year 3 7,895.29, year 4 7,049 rands,37, year 5 6,294.08, year 6 5,619.71, year 7 5,017.60, year 8 4,480, and finally year 9 4,000 as it was deposited because it didn't spend any time and hence it didn't gain any interest whatsoever, and hence the total money that will be in his account after 9 years, we just add up all those values he accumulated throughout the years, and that will give us a total of 59,182.63. Now you can see that even calculating for 9 years is long enough. It's tricky. There's too much room for mistakes. Now imagine if he had waited for 20 years until he withdrew his investment. This calculation will be a nightmare, and hence we need to come up with a simpler way of making these calculations. That is where now we need to derive a formula to make our calculations simpler. Now we know this formula from sum. Sn is equals to a r to the power n minus 1 all divided by r minus 1, where r is greater than 0. This is a summation formula for geometric series. And again, we know that Sn is equals to a 1 minus r to the power n all divided by 1 minus r, for r is less than 1 now. And again, that is a geometric series sum. In the previous exercise, Owen's amount at the end of 9 years is calculated by adding the accumulated amounts for each deposit, and hence 59,102.63 is equals to 4,000 plus all those amounts in between up to 9,983.05. And now, if we line up those calculations in order or in a row, we'll see that it will be 4,001 plus I to the power 0 up until year 8, where it's 4,001 plus I to the power of 8. And we notice something, that this is a geometric series with a constant ratio r is equals to 1 plus I or 1 plus 0,12 in this particular example. Using the geometric sum formula now, we'll have a is equals to 4,000, r is equals to 1,12. That is again 1 plus I, 1 plus 0,12 is equals to 1,12. And n is equals to 9 years. And we're going to use this formula where r is greater than 1. Sn is equals to a r to the power n minus 1 all over r minus 1. And now substituting in my values, I will have Sn is equals to 4,000 or multiplied by 1,12 to the power 9 minus 1 all divided by 1,12 minus 1. And punching that into the calculator will give me 59,102.63 rands. See, this was very simple and straightforward and very less time consuming as compared to the table. And now we need to derive a more general formula now for all the calculations concerning annuities. Therefore, we can use a geometric sum formula to derive a formula for future value f of series of n regular payments of an amount x which are going through an interest rate of I. We will have a is equals to x, r is equals to 1 plus I. And now introducing our formula, Sn is equals to a r to the power n minus 1 all divided by r minus 1. And now substituting in my values, I will have f, which is our future value, is equals to x 1 plus I to the power n minus 1 divided by 1 plus I minus 1. And now the numerator, I'm going to leave it as it is and simplify the denominator. And I can see that on the denominator, the positive 1 and the negative 1 will cancel each other out, leaving me with only I. And hence, our future value formula now will be f is equals to x 1 plus I to the power n minus 1 all divided by I. And that is the formula we are interested in. And now, in that formula, we can simplify it or change it around to make x now the subject to the formula for when we want to calculate the regular deposits, to have this formula which states x is equals to f multiplied by I all divided by 1 plus I to the power n minus 1. Now let me tip you on future value annuities. First tip, timelines are very useful for summarizing and visualizing given information, and hence, where you can, please use timelines. Next, when payments are made multiple times per year, we determine N by multiplying the number of years by P, as you can see me do in this table. Yearly, that is annually, we just multiply the N by 1. Half yearly, semi-annually, we multiply by N by 2. Quarterly, we multiply N by 4. Monthly, we multiply N by 12. And weekly, we multiply N by 52. And finally, daily, we multiply N by 365. And the final tip, use the formula 1 more plus I is equals to 1 plus I to the power M divided by M all to the power of M to convert nominal interest rate to effective interest rate. Now, let's jump straight into an exercise. Esther is planning to send her son back to school in 2 years' time. She makes an itinerary for her son's fees and she expects them to be 40,000. How much must she save at the end of each month if her savings account earns an interest rate of 10.5% per annum compounded monthly? We know that F is equals to 40,000, that's our future amount. I is equals to 0.105 divided by 12. N is equals to 2 multiplied by 12, which is equals to 24. And X, the regular deposits, we don't know. That's what we're trying to calculate. And hence now we're going to introduce this formula to calculate the regular deposits. X is equals to F multiplied by I, all divided by 1 plus I to the power N minus 1. And substituting my values into this formula, now I'll have 40,000 multiplied by 0.105, all divided by 12, all divided by 1 plus 0.105 divided by 12 to the power of 24 minus 1. And that will give me a value of 1,505.04 cents. And hence she must make regular deposits of 1,505.4 cents each month. Now let's take a look at sinking funds. Vehicles, equipment, machinery, and other similar assets all depreciate in value as a result of usage and age. Businesses often set aside money for replacing outdated equipment or old vehicles in accounts called sinking funds. Regular deposits and sometimes lump sum deposits are made into this account so that enough money will have accumulated by the time a new machine or vehicle needs to be purchased or bought. Now let's take a look at this example with the previous information in mind. Zero Academy, an online tutoring company, buys a new laptop for 70,000 rands. The value of the laptop depreciates on a reducing balance basis at 15% per annum. The company plans on replacing this laptop in 5 years' time, and they expect the price of a new laptop to increase annually by 5%. Question number 1. Calculate the value or the book value of the laptop in 5 years' time. Question number 2. Determine the minimum balance of the sinking fund in order for the company to afford a new laptop in 5 years' time. And finally, question number 3. Calculate the required monthly deposit if the sinking fund earns an interest rate of 14% per annum compounded monthly. Let's work through it. Question number 1. Calculating the book value. We know that P is equals to 70,000, I is equals to 0.15, N is equals to 5, and the accumulated amount, that is what we're trying to find. And now we're going to introduce the reducing balance formula. A is equals to P 1 minus I to the power N. Please take note, this is 1 minus I because this laptop is losing value and hence it will have to be minus, not positive. And now substituting in the values into this formula, I will have A is equals to 70,000, 1 minus 0.15 all to the power 5. And that will give me a value of 31,059 rands, 37 cents. Let's move on to question number 2. Determine the minimum balance of the sinking fund in order for the company to afford a new laptop in 5 years' time. We're now going to calculate the cost of new laptop, and then the cost of the old laptop or the depreciated value of the old laptop is 31,059 rands, 37 cents, as you can see on a white rectangle above. Now, I know that in this case, my P is still 70,000 rands, but the interest rate this time around is 5% and hence 0.05, and N is equals to 5 years. And again, introducing my formula now, the new laptop is appreciating. It's not depreciating. It's a new laptop. It's appreciating and hence its value is going to increase. And hence we'll use 1 plus I not 1 minus I as previously used. And now substituting in my values into this new equation, I will have A is equals to 70,000, 1 plus 0.05 all to the power 5, and that will give me an accumulated amount of 89,339.71 cents. This will be the price of the new laptop in 5 years time, when the old one is now worth 31,059 rands,37 cents. And now, in order for the laptop to be able to afford that new laptop, assuming that they sell their old laptop, we calculate the cost of the new laptop as follows, or the cost of the sinking fund as follows. We go on to say they need to have at least a minimum of the difference between the cost of the new laptop and the cost of the old laptop, which is 89,339.71 minus 31,059 rands,37 cents, and hence the company should at least on their sinking fund have 58,280.34 rands in order to be able to afford a new laptop, because that money of the old laptop, the depreciated value, will help them to add into the sinking fund. Now let's move on to question number 3, the required monthly installments. We know that our future value needs to be 58,280.34, which will add to the 31 in order for the company to be able to afford a new laptop. And hence our F is equals to 58,280.34. Our I is equals to now 0.14 divided by 12. And finally, number of years is equals to 5 multiplied by 12, which is equal to 60. And the monthly installments, X, is what we are trying to find. We don't know that yet. And introducing now the formula, X is equals to F multiplied by I, all divided by 1 plus I to the power n minus 1. And substituting in my values now, I'll have 58,280.34 multiplied by 0.14 over 12, all divided by 1 plus 0.14 over 12 to the power 60 minus 1. And that will give me an X value of 676 rands,14 cents. This is the money that they need to deposit monthly for 5 years in order for them to be able to afford the new laptop in 5 years times. And that is how future value annuities work. Now let's move on to present value annuities. That is where, for present value annuities, regular payments are now made to pay back some sort of a loan over a specified time period. Usually the reducing balance is charged compound interest at a certain rate. In this section, we'll learn how to determine the present value of a series of payments. Let's take a look at this exercise to explain this concept a little bit better. Jane needs to withdraw 5,000 rands from her bank account every year for 4 years consecutively for her medical bill. How much must she deposit into her account, which earns 11% per annum, to be able to make those withdrawals possible in the future, assuming that these withdrawals are the only money going out of her account? Let's work through it. We know that A is equals to P 1 plus I to the power of n, making P subject of the formula P is equals to A over 1 plus I to the power of n. And now simplifying that formula a little bit further, we're gonna take the 1 plus I into the numerator, and we know that in doing that, the exponent must change its power, and hence the n becomes negative n, and hence we'll have P is equals to A 1 plus I to the power negative n. And now for a first withdrawal, A is equals to P1 plus I to the power negative n. That is my formula, and substituting in the values now, P is equals to 5,000, 1 plus 0.11 to the power negative 1, because that's the first year. That will give me a value of 4,505.50. Now let's move on to second withdrawal. P is equals to now 5,000, 1 plus 0.11. The year I have changed now is negative 2, because this is the second year, and hence the new value will be 4,058 rands,11 cents. And now for the third withdrawal, the n now is 3. P is equals to 5,000, 1 plus 0.11 to the power negative 3, and that will give me a value of 3,655.96. For her last withdrawal now, the n is now 4. P is equals to 5,000, 1 plus 0.11 to the power negative 4, and that will give me a value of 3,293.65. And hence the total deposit required will be 4,504.50 plus 4,058.11. plus 3,655.96 plus 3,293.65. That will add up to give me a total of 15,512.22. Now we can confirm this by using a table. Here is our table. It will have initial deposit, calculations, and accumulated amount. Initial deposit, we calculated it to be 15,512.22 rands. Amount after 1 year. This is the amount of money in an account after first year. That money we calculated it by P is equals to 1 plus I to the power n. This time n is 1, and hence we will have 15,512.22, the initial deposit, 1 plus 0.11 to the power 1. That will give me 17,218.56 rands. Now, that is the amount of money in an account after the first year before she makes the withdrawal. And now the year has ended, she needs to make a withdrawal. That means we need to now calculate the amount of money in an account after the first withdrawal. The amount after withdrawal will be given by 17,200.56 minus 5,000, because the 5,000 are the regular withdrawals, and now after withdrawing the 5,000 she will have 12,218.56 rands. She has made her withdrawal and now she pauses for a year, and when she pauses the money will be earning interest, and hence we need now to calculate the amount in her account after 2 years. And again we go on and say that money that is in her account after the first withdrawal, which is 12,218.56, all multiplied by 1 plus 0.11 to the power 1, because it earns interest for a year and then she withdraws, and hence the n will always be 1, and that will give us a value of 13,562.60 cents. Now that is the amount after 2 years before she makes the second withdrawal now. And now when she makes the second withdrawal, we're gonna say 13,562 minus 5,000 to give us a new value of 8,562.60 cents. That is the money that will be there after the second withdrawal. And after the second withdrawal, she again pauses for a year, doesn't withdraw anything, and hence the money will be earning interest for a year. And now we need to calculate this interest. Then hence the amount in her account after now 3 years. Again, we're going to say 8,562.60, all multiplied by 1 plus 0.11 to the power of 1. That will give me an account of 9,504.49 cents. That is the amount in her account after 3 years before the withdrawal. Now let's calculate the amount after the third withdrawal, and that will be given by 9,504.49 minus again 5,000 to give us an amount of 4,504.49. Again, she pauses for a year, and for a year this money will be earning interest, and now we need to calculate the new money, and that money after 4 years will be given by 4,504.49 multiplied by 1 plus 0.11 to the power 1 to give us a new amount of 5,000 rands. This is the amount in her account after the 4th year, and now she makes the last withdrawal, and hence the new money will be 5,000 minus 5,000, leaving the account with 0 money. She has achieved her goal. She has made her 4 deposits or her 4 withdrawal possible, and now her account is empty, but her goal is met. Now again, these calculations using tables and everything are a headache. They are long, and this is just for 4 years. Imagine now if it was for 30, 20 years, it would have been damn near impossible. And again, we need to derive some sort of a formula to simplify our lives. Now let's derive the formula. Again, in the exercise above, Jane had to deposit 15,512.22. that is 5,001 plus 0.11 to the power negative 1 up until 5,001 plus 0.11 to the power negative 4. And again, if we look at this now, we can notice that this is a geometric series with a constant ratio 1 plus 0.11 to the power negative 1. But this time around, the constant ratio r will be less than 1. Using the formula for geometric sum, we we're gonna have A is equals to the first value 5001 plus 0.11 to the power negative 1, R the constant ratio 1 plus 0.11 to the power negative 1, and N the period of investment is equals to 4. And introducing the formula for R is less than 1, Sn is equals to A 1 minus R to the power N all over 1 minus R. Now, substituting in everything I know, I will have Sn is equals to 5001 plus 0.11 to the power negative 1, all multiplied by 1 minus 1 plus 0.11 to the power negative 1, all to the power 4, all divided by 1 minus 1 plus 0.11 to the power negative 1. Now, before we punch that into our calculator, let's simplify it a little bit further so that it becomes simpler to punch into our calculator, and hence it will help us derive the new formula or general formula a little bit better. Now, the first thing I'm going to do, that 1 plus 0.11 to the power negative 1 that is on the numerator next to the 5000, I'm going to take it to the denominator so that it will have a positive exponent. And that 4 that is inside the square bracket, I'm going to multiply it to the exponent of negative 1 so that it becomes negative 4, and hence my calculation will be a little bit now shorter. And doing everything I've just told you, I'll have Sn is equals to 5000 because that 1 plus 0.11 to the power negative 1 is now at the denominator. The 5000 will multiply the square bracket 1 minus 1 plus 0.11 to the power now negative 4, all divided by the 1 plus 0.11 that has ascended down to the denominator, all multiplied by 1 minus 0.11 to the power negative 1. And now, this time around, the numerator is simplified enough. I'm going to leave it as it is and focus on the denominator. On the denominator, inside the square bracket and outside, I notice that there's 1 plus 0.11 and also inside there's 1 plus 0.11, and hence I'm going to multiply that circular bracket into the square bracket. 1 plus 0.11 multiplied by 1 will still be 1 plus 0.11. And now 1 plus 0.11 multiplied by 1 plus 0.11 to the power negative 1, that falls all to become 1 because the power of 1 and the power of negative 1 will cancel each other out. To give us a power of 0, and that will reduce to 1. Anything to the power of 0, we know it's 1. And doing everything I've just said, I will have Sn is equals to 5001 minus 1 plus 0.11 to the power negative 4. Again, the numerator is unchanged. And now we will have for the numerator 1 plus 0.11 minus 1, because again, 1 plus 0.11 multiplied by 1 is the 1 plus 0.11. And 1 plus 0.11 multiplied by 1 plus 0.11 to the power negative 1 becomes 1. And the negative sign is the sign that's in between the values. And simplifying the denominator again, that is the 1 and the negative 1 will cancel each other out, leaving us with Sn is equals to 5001 minus 1 plus 0.11 to the power negative 4, all divided by 0.11. And that will give us a value of 15,512.22. And again, you can see that this is a much simpler calculation than the table 1. And now let's derive a more general formula now for all present value annuities related problems. We can therefore use the formula for the sum of geometric series to derive formula for present value P of series of n regular payments of an amount X which are subjected to an interest rate I. And hence we know that our A becomes X 1 plus I to the power negative 1. R is equals to 1 plus I to the power negative 1. Before I continue, I just need to stress to you, the steps here will be the very same steps we followed throughout the last example, and hence, if you didn't understand the last example, there's no need to go back to it, just listen very carefully here. Or if you did understand it, just make sure that you emphasize your knowledge. And again, introducing the summation formula for R is less than 1, Sn is equals to A 1 minus R to the power n, all divided by 1 minus R. And now substituting in everything into my formula, the Sn becomes the P, that is the present value is equals to X 1 plus I to the power negative 1 multiplied by 1 minus 1 plus I to the power negative n all to the power n, all divided by 1 minus 1 plus I to the power negative 1. And again, looking at the denominator, the 1 plus I to the power negative 1, that is next to x on the numerator rather, I'm going to take that into the denominator so that it will have a positive exponent. And inside the bracket, the negative, or inside the square bracket on the numerator, the negative 1 and the n are both powers or exponents, and hence I can multiply them out. They will multiply out to give me a power of negative n, or a single power of negative n. And now, doing everything I've just said, I will have p is equal to x multiplied by 1 minus 1 plus I to the power negative n, all divided by 1 plus I, 1 minus 1 plus I to the power negative 1. And this time around, the numerator again, I'm going to leave it alone and simplify the denominator. I'm going to multiply the circular bracket into the square bracket, that is 1 plus I multiplied by 1, and again 1 plus I multiplied by 1 plus I to the power negative 1. The 1 plus I multiplied by 1 will still give me 1 plus I, the negative sign, I'm going to write it down as it is, and then 1 plus I multiplied by 1 plus I to the power negative 1, they will cancel each other out to give me 1. Because their powers are negative 1 and 1, then they will add up to give me 0, and we know that anything to the power of 0 is 1. And doing everything I've just said, I will have p is equal to x multiplied by 1 minus 1 plus I to the power negative n all over 1 plus I minus 1. And again, simplifying the denominator a little bit better, the 1 and the negative 1 will cancel each other out to give me 0, and hence I will now have p is equal to x 1 minus 1 plus I to the power negative n, all divided by I. And that is the formula that we are now interested in. P is equal to x multiplied by 1 minus 1 plus I to the power negative n, all divided by I. And now, in that formula again, we can make x subject of the formula to have this new formula, x equals to p multiplied by I, all divided by 1 minus 1 plus I to the power negative n. Now, let's take a look at an example. Owen takes out a student loan for his final year of mechanical engineering. As per the loan agreement, the repayment period is 1.5 years for each year of financial assistance, given that the loan is subjected to an interest rate of 12% per annum compounded monthly. First, calculate if Owens pay a monthly installment of 2,100. Calculate the loan amount. Second, calculate how much interest Owen is due to pay on his student loan after 1.5 years. Let's work it out. Again, we know that x is equal to 2,100, I is equal to 0.12 divided by the period, that is 0.12 divided by 12. N is equal to 1.5 multiplied by 12, which is 18 months. And introducing our formula now, P is equal to x 1 minus 1 plus I to the power negative n, all divided by I, and substituting in everything I already know, that is P is equal to 2,100 all multiplied by 1 minus 1 plus 0.12 over 12 to the power negative 18, all divided by 0.12 over 12, and that will give me a present value amount of 34,436.36 cents. That is the amount that Owen owes. Second question. Calculate how much interest Owen is due to pay on his student loan after 1.5 years. And now, in order to do that, we're going to go on and say interest paid is equal to, first, let's calculate the total amount he paid. He paid 2,100 multiplied by 18, that is 37,800 francs. That is the amount that he will end up paying to the bank. And now, his loan amount was 37,436.36, and hence we need to find the difference between those two values, that is 37,800 minus 34,436.36. that will give us an amount of 3,363.64 cents. That is the total interest that he paid for his loan. Now, let's move on to analyzing investments and loan options. In the exercises below, we will assess the effects of loan period on the total amount that needs to be paid back. Now, let's take a look at the exercise. Tabo takes out a vehicle finance loan of 500,000 rands with an interest rate of 12% per annum compounded monthly. Question number 1. Calculate the monthly repayments for a repayment period of 5 years, 60 months. Question number 2. Calculate the interest paid on the loan at the end of the 5 years period. Question number 3. Determine the monthly repayments for a repayment period of 7 years, that is 84 months. Determine the interest paid on the loan at the end of the 7-year period. Question number 5. What is the difference in the monthly repayment amounts? Question number 6. Comment on the difference in the interest paid for the two different time periods. Now, let's work it out. Question number 1. Monthly repayments after 5 years. We're gonna go on and say our P is equals to 500,000, I is equals to 0.12, all divided by 12 because it's compounded monthly and hence we divide by 12, and our N is 60 months. And now introducing our present value formula, where X now is the subject of the formula. X is equals to P multiplied by I, all divided by 1 minus 1 plus I to the power negative N. And substituting in our values, we'll have X equals to 500,000 multiplied by 0.12 over 12, all divided by 1 minus 1 plus 0.12 over 12 to the power negative 60 to give us X values of 11,122.22 cents, and hence this is the amount he needs to pay monthly for 5 years, that is 11,122.22 rands. Now let's go on to calculate the interest paid on the loan at the end of 5 years. To do that, we know that he has an installment of 11,122.22 for 5 years, and hence the interest paid will be calculated as follows. First, we'll calculate how much total he paid. That is, the total amount paid is equal to 11,122.22 multiplied by 60 to give us a value of 667,333 rands 20 cents. That is what he ended up paying. And now his loan value was 500,000, and hence we need to find the difference, that is the interest paid, and that is calculated by 667,333.2 minus 500,000. That will give us an interest paid of 167,333.20 cents. Let's move on to question number 3. Determine the monthly repayments for a repayment period of 7 years. Now, for this new calculation, we still use the very same formula. X equals to P multiplied by I, all divided by 1 minus 1 plus I to the power of negative N. And we know that this time around our P is 500,000 still, 0.12 over 12, but what has changed is the number of years is now 82, the N is 82 now, and hence we have X is equals to 500,000 multiplied by 0.12 over 12, all divided by 1 minus 1 plus 0.12 over 12 to the power negative 84. And that will give us a value of 8,826.37 cents. That is the monthly installment for the 7 years period. Now, determine the interest paid on the loan at the end of the 7-year period. Again, like the last time, first we calculate how much total he ended up paying using these installments for 84 months, that is 8,826.37 multiplied by 84. That will give us a value of 741,415 rands 8 cents. And calculating the difference to find the interest paid, we'll have 741,415.08 minus 5,000 rands. That will give us an interest value of 241,415.08 cents. Question number 5. What is the difference in the monthly repayment amount? That we're gonna calculate the difference between installments, and hence that is 11,122.22 minus 8,826.37. That will give us a value of 2,295.85 cents. Comment on the difference in the interest paid for the two different time periods. Now, to comment, we know that the 7 years term reduces the monthly installment by 2,295 85 we've calculated for that value. However, it increases the overall interest paid. Hence, longer periods significantly increases the cost. If you mention anything about the difference in interest paid, total interest paid, and the difference in monthly installment, you should be able to get full marks for a question like this. And hence, that brings us to the end of this lesson. Thank you for joining me. Please do comment below on which chapters you want to see me cover next. But for now, take care.